All right, let's dive in. In this explainer, we're going to tear down a real-world, grid-tied solar PV system, and we're going to do it using its official engineering blueprint, the Bill of Materials. We'll break it down piece by piece to see exactly how it all comes together.
Okay, so here's our game plan. We'll start with the Bill of Materials itself, the master list, you could say. Then we'll walk through each major part of the system, how it generates power, how it converts it, and how it stores it. After we check out all the supporting gear, we'll put it all back together to see the whole system in action. First up, the system blueprint. Before we can really get into the nuts and bolts of the system, we have to understand its parts list, and that's where the Bill of Materials comes in. It's really the foundation for this whole analysis.
So what exactly is a bill of materials, or a BoM, as you'll often hear it called? Well, in the engineering world, it's the master shopping list for any project. It's a super detailed, itemized list of every single thing you need for construction. I'm talking everything from the big-ticket items right down to the last screw and washer.
And this isn't just some textbook example. The BoM we're digging into comes from a real-world project by Rahama Fru's Renewable Energy. This is great because it grounds our entire breakdown in actual engineering practice, not just theory.
All right, let's get to the heart of it. Our first major stop is the generation core. This, as you can probably guess, is where all the magic starts, where the energy is actually produced.
So what's its job? In strict engineering terms, the photovoltaic array has one very specific function: to take solar radiation, that's the sunlight hitting it, and convert it directly into DC or direct current electrical power. That's the photovoltaic effect in action.
And take a look at the detail in the BoM. It doesn't just say, get some solar panels. No. It calls for exactly 35 units of a specific model, the LONGi 610-watt peak. This kind of precision is absolutely critical if you want to design and model a system that's going to perform the way you expect it to.
Okay, so let's do some quick math here. If we multiply the number of modules, that's 35, by their individual power rating of 610 watts, what do we get? We get a total peak DC capacity of 21.35 kilowatts. Now that number is a really important design parameter. It tells us the maximum power the array can possibly pump out under ideal test conditions. So, we've generated a bunch of DC power. Great. But what's next? Well, we've got to manage it and convert it into something we can actually use. And that brings us to our next big piece of the puzzle, the power conversion and control subsystem. This part of the system is a real workhorse. It's got two super important jobs. First, it takes that DC power from the panels and inverts it into the AC, or alternating current power, that our buildings run on. And second, it acts like the brain of the whole operation, managing and monitoring everything to make sure it's all running smoothly. To get this done, the BoM lists two key pieces of equipment. There's one big 50-kilowatt Growatt inverter to handle the heavy lifting of power conversion, and then there's a Growatt Shine Master, which is the monitoring system that keeps an eye on everything and logs all the data. These two really work as a team to control the system's output. Now here's something really interesting. The inverter is rated for 50 kilowatts, right? But remember, the solar array's peak capacity is only 21.35 kilowatts. Why the huge difference? Well, this is a deliberate engineering choice called oversizing the inverter. It's a smart move that allows for future expansion. You can add more solar panels later on without having to rip out and replace the inverter.
Okay, moving on. Let's talk about the part of the system that gives it resilience and keeps the lights on when the grid goes down, the energy storage unit.
From an engineering perspective, the ESU has two main goals. It's there to soak up and store any extra solar energy that's generated but not used right away. And even more importantly, it provides a seamless backup power source if the main utility grid ever fails.
The BoM gets pretty specific here, calling for a complete energy storage system, or ESS, and check out the performance specs. They're spelled out clearly. It has to be able to handle a load of at least 3 kilowatts and provide a minimum of 6.9 kilowatt hours of backup. The document even specifies the battery chemistry, LFP, or lithium iron phosphate. That's a big deal because LFP batteries are known for being incredibly safe and having a really long lifespan. And of course, this unit comes with its own dedicated 3.5 kilowatt hybrid inverter.
That number, 6.9 kilowatt hours, is a huge deal. It's a key performance metric that tells you exactly how much energy the system can deliver to your essential stuff during a blackout. For the person actually using the system, this number translates directly into how many hours, or maybe even days, they can operate off-grid.
All right,
We've covered the big three: generation, conversion, and storage. But how do we actually connect all these pieces together? Well, that's where the balance of system, or BOS, components come in.
Balance of system is the official engineering term for, well, pretty much everything else. You know, the solar panels and the inverter get all the glory, but the BOS components are the unsung heroes. We're talking about the mounting racks, the wiring, the safety gear, all the stuff that's absolutely essential for a safe, reliable system that's going to last for decades.
So let's break that down. First up, you've got the structural parts. This includes the main mounting structure, which is specifically designed for a reinforced concrete roof, and then you have all the hardware that goes with it. The pipes, the industrial channels, the clamps, and every last screw and plug needed to physically anchor those 35 solar panels.
Then, of course, you have all the components that actually move the electricity around, and this list is pretty long. It covers everything from the heavy-duty power cables and grounding wires down to all the different kinds of cable lugs you need to make solid connections. It even includes things like conduits to protect the wires, cable ties to keep things neat, and heat shrink and tape for proper insulation.
And last, but definitely not least, are the critical safety components. This system is packed with layers of protection. You've got a beefy 125-amp molded case circuit breaker from a top brand like Schneider, an AC distribution box, and array junction boxes. These aren't optional. They are absolutely non-negotiable for ensuring the system operates safely.
Okay, for our final section, let's pull it all together. We've looked at all the individual parts from the bill of materials, so now let's see how they work together as one single integrated system.
Let's trace the path of the energy from start to finish. Step 1. The solar array creates DC power from sunlight. Step 2. The array junction box gathers that power from all the different panel strings. Step 3. The main 50 kilowatt inverter steps in and converts that DC power into usable AC power. Now running in parallel is Step 4. The energy storage system, which can either be charging up with extra DC power or discharging power through its own hybrid inverter. And finally, Step 5, the AC distribution box takes all that usable AC power and safely sends it where it needs to go, either to the building itself or back out to the utility grid.
So, as you can see, breaking down this bill of materials shows us that it's so much more than just a shopping list. It's really a story of engineering decisions. Every single component on that list was chosen for a reason, representing a calculated trade-off. And that brings us to a final thought to chew on. How do engineers use a document just like this one to strike that perfect balance between competing demands, things like system performance, long-term reliability, and of course, the project's budget?